in this video, I'm going to teach you guys how to use a proof by contrapositive and also when you should use the proof by contrapositive, because knowing when you use a specific proof technique matters. All right, knowing which technique to use matters. But the three proofs I'm going to cover in this video are the ones listed on the screen right now. If n squared is odd, then n is odd. If n squared is irrational, then n is also irrational. And if 3 times n is divisible by 6, then n is even. And these are the three proofs I'm going to be doing with a proof by contrapositive. So let's solve this using a proof by contrapositive. So we need to prove if n squared is odd, then n is odd. And see how I wrote this in the conditional form? This is going to be important. All right, if you try to use a direct proof, this will not work out. And you could try it out, right? You can represent n squared as 2k. I'll give you a hint. 2k plus 1, right? Since n squared is odd, you can represent it as 2k plus 1. If you start off like this, there's really no way that you can get n is odd. There's no way you can conclude that, right? Or there probably is a way with the direct proof. I'm not going to state absolutes, but it's probably going to be a lot harder than proving the contrapositive. And let's go ahead and write the contrapositive of this. What's the contrapositive of a conditional? Well, the contrapositive is if we have p dash q, then it's not q dash not p. So first off, you flip the condition and the conclusion, and you also invert both of them. So this right here is the contrapositive. So what do we do? Well, we should flip this condition. So n is odd, n squared is odd. So let's write down n, oops, I did control x. N is odd dash n squared is odd. Right now this isn't the contrapositive yet, and we need to take the inverse of both. So what's the inverse of an odd number? Well, the inverse of an odd number is n is even. So n squared is also even, right? We need to take the inverse of both sides, right? The inverse of n squared is odd. It means the inverse of n squared is odd. The statement, the inverse of the statement is n squared is even. Okay? So this right here is the contrapositive, and this right here is like the middle segment. We can ignore that. Now, why is the contrapositive important? Why are we using contrapositive? Why aren't we using converses or inverses, right? Well, here's the thing. With contrapositive, if the contrapositive is true, then the original statement is true as well. So we can kind of toss this original conditional away, and then we can prove this new statement here. And if we prove this, it proves the original statement. So this right here is a lot easier to do, and hopefully you guys see that with your even and odd proofs. But let's go ahead and save this down here, and let's go ahead and start the proof. So for the sake, so you can start off, maybe let them know it's a contrapositive. You don't have to, depends on the class rules. But let's write down for the sake of contrapositive, we will prove that if n is even, then n squared is even. And remember, if you prove this guy, then you also prove this guy. Okay, so now that we have that written down, we can erase the original statement down there, the original contrapositive, because we have it in the proof. And so look at this. For the sake of contrapositive, we will prove that if n is even, then n squared is even. Here's the thing. You don't necessarily have to write down for the sake of contrapositive. That's completely up to you or completely up to your course. My professor likes it when we do that. I don't think they'll take off points for it, but do as you wish. And after this, what do? Well, for just like any even or odd proof, we know that n is even. So since n is even, n can be equal to 2k, where k is an integer. Okay? Any integer, right? This is the definition of even numbers. Correct? 2 times an integer is equal to that number, n. Okay? Once we have this, what do? Well, substituting, right? We can substitute into n squared. So substituting n into n squared we get 2k squared. All right? So n was equal to 2k, and all we did was substitute 2k into n squared as n. Right? So now we have 2k squared. Once we have this, we can say, and we can remove this period. Let's put an equal sign, which is equal to 4k squared, which is also equal to 2 times 2k squared. And you'll see why I do this later. Well, by the, let's say, since multiplying, I spelled that wrong, multiplying int gives int, 2k squared is an int. Alright, so 2k squared is an integer. Well, here's the thing. Is this not the definition of an even number? Remember, we substituted n, so we assumed n was even, and we substituted 2k into n squared, right? And the reason why we can use 2k is because since we assumed n is even in the condition, since we assumed n is even, we can represent it as 2 times the integer. Once we substituted n into n squared, we got 2k squared. Here's the thing. We can, do a little bit of algebra to get 4k squared, and we get 2 times 2k squared. Now, I wrote down, since multiplying ints gives ints, 2k squared is also an integer. Well, here's the thing. We have an integer here, and that integer is multiplied by 2. So that means, remember, this was n squared before. That means when n is equal to 2k, or when n is an even number, n squared is also an n squared is also an even number. So we can write down, by the definition of even numbers, n squared is also even. And there you go. Now, you could write a conclusion. You could say, if n is even, then n squared is even, or we have proven this, right? I'm not necessarily going to write, I'll just explain the conclusions to you, since I don't even know, it depends on the class. Because my class doesn't care if you write down, like, since we proved the contrapositive, the original contrapositive is true. No, they just want us to write down, like, they just wanted to rewrite this up here, the actual contrapositive. And I think the reason why they do that is because if you've proven this, then you will automatically proven the original state, which is the contrapositive of this guy right here, right? So if I were to conclude this, I would probably say, by the definition of even numbers, n squared is also an even. Therefore, if n is even, then n squared is also even. Now, here's the thing. Again, it depends on the class. Some of them might say, because we have proved the contrapositive, right, then the original statement is true. Okay, so just keep that in mind. It can probably differ depending on who's instructing or the rule set of your class. So this one is pretty obvious which technique we're using, and the technique we're using for this is proof by contrapositive. Now, besides the fact that the point of this video is to teach you how to do proofs by contrapositive, which probably makes it even more obvious which technique we're going to use. If you see something that says irrational in the proof, you're likely going to be using a proof by contrapositive. And later on, you might be using a proof by contradiction if you have learned that yet. And that's amazing. But if you haven't, then that's something in the future. But keep in mind, if you see irrational in your proof, you can't really prove this with a direct proof, okay? You're likely going to use a proof by contrapositive, and that's because an irrational number is just something that's not rational. So it's going to be pretty hard to prove something is not rational. But n squared is irrational, right? And the condition is n is irrational. Okay. This is not centered. But this right here is our statement in conditional form. So if n squared is irrational, then n is also irrational. What's the contrapositive of this? Remember, we flip the condition in the conclusion, and we invert both of them. So what is that? What is the contrapositive of this? Well, the contrapositive of this is, if n is rational, then n squared is rational. Amazing. Okay. This one looks quite easy to do. So we can write this down at the bottom. Let's write down for the sake of contrapositive. Now, just saying, I don't think anyone's actually going to word it like for the sake of contrapositive. I think most people are going to say for the sake of contradiction when they're doing a proof by contradiction. I just say for the sake of contrapositive. I'm like, I guess your grammar doesn't really matter as long as you get your point across in a proof, in an introductory proof course. You'll probably get full credit. So for the sake of contrapositive, we will prove that if n is rational, then n squared is also rational. So what do we do with this? Okay, what do we do with this? Well, what's the definition of a rational number? Well, by the definition of rational, let's say n is equal to a over b, where terrible. I just wrote that where in one stroke. Let's write the letter separately to make it comprehensible. Where a, b are integers. Okay? Ints. Right? This is the definition of a rational number. We have an integer over an integer. If your number can be expressed as that, then you have a rational number. All right. Once we have this, we can substitute. So substituting n into n squared, we get a squared over b squared. Okay? Here's the thing. A squared over b squared. This looks like awful lot like a rational number, right? N squared expressed as a over b. This looks like a rational number. Well, how do we show that? Well, the definition of a rational number is an integer over an integer. So we need to state that a squared and b squared are also integers. What rule do we use for that? Well, we use the axiom. We use the integer axiom. So let's say multiplying integers, or technically squaring them as well, ints gives ints where a, b are, hold up. I'll get back to, I made a little mistake in the previous thing, but I'll get back to that. Multiplying ints gives ints. Therefore, a squared and b squared are ints. Okay? Now, here's the mistake I made. I need to state where a, b are ints and b is not equal to 0. Okay? Since a over 0, that b 0 is an integer, right? Here's the thing. You can't have a fraction with an integer over 0. That does not exist. Come on. Something over 0, you learn that. You guys know what I'm saying, right? So make sure you include this part. I very easily forgot that. So hopefully you guys don't very easily forget that when you're taking your tests. But remember to put this, okay? Make sure you state that the bottom integer, the denominator integer, cannot equal 0. It's very important. Right? Are ints where b squared is not equal to 0. All right? Make sure you remember to state that. Okay? And we have proven this by the definition of rational. N squared is rational when n is rational. So this is our proof. Okay? Pretty simple. We just write down the contrapositive in the introduction, and then we go on with our logic and just prove the contrapositive. Remember, again, as I said, it's optional if you want to write down, since we proved the contrapositive of blank so-and-so statement, the original statement is also true. I mean, like, you can state that in your conclusion. I would recommend it. You know, it doesn't hurt to state that. But anyways, let's move on to the next problem. All right, this is the last problem. And I know what you're thinking. Why can't I do more problems with computer engineering, Jitty? His voice is so amazing. It's so beautiful. I know. Thank you. You don't have to compliment me. I already know that. Anyways, let's continue on with the problem. Let's write this down in conditional form first. So 6 3n dash n is even. So what do we write here? We wrote down that if 3n is divisible by 6, so this is a divisible symbol if you don't know that. It just stands for 3n is divisible by 6. All right, then n is even. Okay, well, you can't really do this. Well, we can't really define this with any specific integer. So what do we need to do? We need to take the contrapositive. All right, right? Divisibility, this really has no definition that we can go off of to conclude n is even. Right? So let's go ahead and take the contrapositive. And the contrapositive is n is odd, then 6 is not divisible by 3n. All right, so we need to prove this statement here, and if we prove this contrapositive, then we prove the original statement. So let's go ahead and set up the proof. Let n be an integer, okay? And I'm not going to write down for the sake of contrapositive anymore. Let's write down, we will prove that if n is odd, then 3 times n is not divisible by 6. Let's go and plug my phone, because for some reason this charger gets me to 81% in like 15 minutes, and I was just at 20%. So I don't want my phone to like dead ass explode. But this right here is our proof, and I just realized I made a mistake throughout the entire video. I'll put that in the edits, but let n be an integer. I'd never introduce the variable n at the beginning of the proof. So don't make that mistake as well. I will put that in the edits later. But let n be an integer. We will prove that if, and this is the contrapositive. Okay, well, we can use the definition of odd numbers. So by the definition of odd, n is equal to 2k plus 1, where k is an arbitrary integer. Okay? All right, what do we have next? Well, we can express the divisibility, right, by the definition of divisibility as an equation. So by definition of divisibility, 3 times n is not divisible by 6 can be turned into 6 times some integer j is not equal to 3 times n. All right, where j is an int. Is an integer. Now, if you don't know where this comes from, okay, I explained this in my axioms video. Link will be down in the description. And I also have, other videos. I don't know. I'll probably put the relevant videos in the description that are related to this, like how to find a contrapositive. Okay, but just take a look at that if you don't know any of it. Maybe I should have said that at the beginning of the video. Yeah, these are, I guess you can tell, disorganized. These videos are, I'm not gonna lie, I make the problem sets like 5 minutes before I record. But let's see, by the definition of divisibility, okay, this is all in check. All right, now that we have this, we can substitute n. So let's substituting n, we get 6 times j is equal to 3 times 2k plus 1, and this becomes 6 times j is equal to 6k plus 1 plus 3. Sorry. All right, well, here's the thing, these will never work. Okay, there's no pair, there's no arbitrary integer j and k that can make this work. Okay, as long as j and k are integers, this equation can never hold true. Now, why is that? Well, let's say j is equal to 1. So let's say j is equal to 1, so we just have 6 on the left. Now we have this equation here. Is there any integer k that we can do this with? There's none, right? If k is equal to 1, then we get 6 plus 3. And that's equal to 9. And if k is equal to 0, then we get 0 plus 3. But that's equal to 3. And 3 is clearly not equal to 6. And 9 is clearly not equal to 6. So j equals 1 doesn't work. Now, why would this never work? Well, this will never work because no matter what value integer you put into k and j, okay, you add 3, right? So if j and k are equivalent, so if j and k are equal to each other, right, let's say j is equal to, let's give an example, j is equal to 3 and k is equal to 3, right? We get 18 is equal to 18 plus 3. Here's the thing, 18 is not equal to 21. This will never work. Oh, I forgot to put not equal to here and not good here. Sorry. I'll put an edit for that as well. But this will never work. There's no integer j or k that can allow this to happen. Therefore, when n is odd, 3n is never divisible by 6. So as long as n is odd, 3n is never divisible by 6. And we can explain that by saying no matter the value j or k, there will always be remainder or a remainder of 3. Therefore, if n is odd, okay, if n is odd, then 3n is never divisible by 6. And again, this looks like jork. Oh my god. I didn't even realize that. Wait, let's separate the k and the j a little more. That's not intentional. I'm not gonna. That's like jork. Oh shit. But that looks like jork. Okay, ignore it. Let's switch the k and j placement. Let's switch the j and k placement. Let's put k here and j here. All right, that's suspicious. Okay, so this right here is the proof. And again, you can conclude this however you want, as long as it aligns with your class's grading policy. But anyways, if you have any questions, put it in the comment section. If you found this video helpful, consider subscribing and liking the video. On a final note, you guys gave me more subscribers than the pounds I can lift on deadlift. Wow, I didn't think I would hit it this fast. I genuinely thought that I would hit like 400. I was hoping for 400 by winter break, but you guys exceeded 600. I think it's at 622 right now. Don't quote me on that. But anyways, thank you everyone. I've been getting a lot more views lately, so I'm very happy about that. And I can't wait to post more in-demand videos in winter. I'll see you then.